Okay, Apurva's here. We're missing Rachna and the others.
Never joined, so actually she was the one who reminded me. Okay.
The other people from Stella just vanished. I don't think any of them responded to any messages after, which is the other two. Pratibha and one more.
Actually, she issue with like in her home, so she couldn't like do it. But
I
she said
can't
like
hear
she.
you. I'm so sorry. The connection's a bit
Okay.
spotty.
Okay. Wait.
Sorry, Pooba, what did you say?
Am I audible now?
Yeah.
Yeah.
Okay. So Pratibha said she wasn't able to contact you because she had something going in her home. So yeah, she
Okay.
said that she will return to you soon, like after going through the sessions. Then
Sure. Okay. So she's not coming for this session.
I'm not sure. She will come, I think so, because
She said she is coming.
What about Ashmi? Do any of you know?
Ashmi, I need to ask her. Okay, maybe I will ask her.
I'm wondering because if everyone said they want to do GR and we're holding a session on GR, it's a bit. I'm not able to understand why they won't turn up for that, or say they're coming or not coming. Is Pugal alive? Pugal is dead. Yeah, are we expecting anyone else?
Rishi is not picking up the call also.
Okay, let me share my screen. Sorry, yeah. So just these two. I'll hold a tutorial class if you want to go over them. If you think everyone was clear. Yeah, let me ask you this way. Apurva, Rachna, and Yuvraj. Just have a look at the solutions that Pugal has uploaded. And out of all of them, the most important question that I've given you is 1D. And I think Pugal will put up my solution to 1D, which is just basic index manipulation. It's working with the Kronecker delta and understanding how you use it. And I hope I put it across in a pedagogical and easy to read format. So if you go through 1D, what you're going to learn there will apply to GR, and going forward, that should help you. So should I share my screen today, Pugal? Okay. I think you have to disconnect yours before. Okay. Okay. Do you see my the notebook?
Yeah.
Okay. So let's start. What we're going to do today is start with GR, and hopefully this is exciting. We're going to start off with this as the definition. I think today I planned to go over where you use the four vectors in electromagnetism and particle physics, but it's unlikely I can finish all of that in 3 hours. So I think those make sense to have a different session for. So today what we're going to do is just focus on understanding the basics of GR. And my plan for today is to give you a quick outlook of what we want to be doing, a plan for how we're going to go about it. And hopefully at the end of today, we should be reaching and trying to understand what tensors are. But if we can't, then that's okay. Right. So if you can see the screen that I've put up right now, what I've written at the top is something that I want you to write down and think about. Okay. So this definition is probably the best definition I've found online while searching, and it comes from this German professor named Friedrich Schuler. And so when we study GR, okay, we're going to be trying to make sense of space-time. And all of you, when you've read popular science, I'm sure are familiar with either movies from Interstellar or anything that you've read in popular science. It turns out that all of the matter content that you can talk about in a system has a very strong relation to the geometry and the gravity of the situation, of the system at hand. So if we understand either the matter content or we understand the geometry of a particular system, there's an interplay between the two, and this interplay is given to us by Einstein's equations. I hope all of you that wanted to study GR and general relativity and gravity in general are familiar with this, because this is typically what all of us, I think me included, when I got interested in theoretical physics, you see movies like Interstellar and you see, wow, okay, gravity has something to do with curvature and the bending of space-time, and that's probably something that all of us across the board have seen and read, and is what draws us to physics. So, do you agree with this, Bhargava? Is this idea new to anyone about the interplay between geometry and matter and what gravity is?
This is quite familiar with us, but not in a deep way, but still it's familiar with us. By the way, I just have a question here. So what does this partial free connection means?
Exactly. Okay. So before we get ahead of ourselves, the reason I've written this out is that what I wanted to say is I hope the starting point is clear. Like, I hope like somewhere we've fallen in love with physics and fallen in love with gravity, knowing that there's some interplay between geometry, curved space, whatever that means, and Einstein's equations, right? So the goal of GR is to understand this. And I think for those of you that don't have noise on your mic, you can unmute yourselves, because I'd really like participation, because currently what I've done is I'm looking at my screen, so I can't check Discord. I have to kind of change tabs to understand who's here, who isn't. So just feel free to unmute yourselves and hop in whenever you like. So the starting point for today is that space-time, I just want you to go over each word, because when we work in GR, it's extremely crucial we slow down and we understand everything that we're writing about, because each word that I've written down has a fundamental consequence to our equations that we're working with. Okay, so if you see the definition I've written for space-time, I've written some words in green and two words particularly in red. Okay, so I'm just going to read it out to you and explain why these particular keywords are important and what they mean. So space-time is a four-dimensional topological manifold, don't know what that means, with a smooth atlas, no idea what that is, carrying a torsion-free connection, God knows, compatible with the Lorentzian metric. By now you should be thinking, Lorentzian, I know something like that. We did something called a metric and something Lorentzian last week, and a time orientation satisfying the Einstein equations. Okay, so the goal of this course is whenever you're doing any sort of study with GR, the goal of GR is to understand what each of these words physically mean, because general relativity is the interplay of how all of these words that I've written down right now constrain and change the equations that we write down to describe space and time. Okay, so from last week, space-time should be a word that isn't new and unfamiliar to you. We may not have done physics in the four-vector formalism, but when I say space-time, you must immediately know that no longer are we talking about time being separate from space, but any kind of event or any kind of phenomenon that I write down has to have space and time connected, which means immediately what you should be expecting is four-vector formalism, right? The next word is four-dimensional, and that's important because it has vast significance with the physics that we're doing. If you change the dimension of the physics that you're working in, you'll find that the number of objects that we use, we say manifolds, okay? It's a very, very interesting phenomenon that out of the many manifolds that exist mathematically, we search for a particular set of manifolds to use, and we say these are the ones that we're interested in. And it's a very curious phenomenon that if we work in two dimensions, okay, the number of manifolds that fit our purposes, where we can say, that's exactly what I'm looking for mathematically, are like, there are only like 4 which satisfy all our conditions. In 3 dimensions, there might be something like 6 possible manifolds. But the crazy curiosity in mathematics is when you look at 4-dimensional manifolds, there are an infinite number that satisfy our needs. So it's, every word in this definition has a point. Smooth atlas, no idea what that is. Torsion-free conduction, in the future, in the coming weeks, you'll understand. Lorentzian metric, we'll understand what that means. So the idea is we can't take any space-time that we want. A space-time that whatever we do physics on, the space-time that we call it, is something that satisfies all the conditions that I've just written down in the definition. It's four-dimensional, it's a topological manifold, it has a smooth atlas, it carries a torsion-free connection, and everything else that I've written down. And it satisfies the Einstein equation. So the goal when you're doing GR is to understand what each of these words mean. Okay? And the resources that I've given down is that if you're a layman new to the subject, you may have heard of Leonard Susskind's lectures on YouTube. While they're intuitive and great, they're not valued at any level if you're trying to pursue physics seriously. The level that I'm going to be pitching this course to you is at the level of Sean Carroll and probably at the level of undergraduates. And hopefully, if you guys want to do GR and you really want to work in research and try to understand papers and pursue your own theories of black holes, that level isn't going to cut it. The more advanced courses are Schuler's lectures. You could look at David Tong's fantastic lecture notes at Cambridge, if you Google them. As well as, this is probably the biggest textbook in all of physics. Okay, it's called Gravity or Gravitation by Missner, Thorne, and Weaver. And this is a huge book. It's about at least 2,000 pages long. And so you're never expected to understand it, but if you ever have a concept or a question in gravity and you're wondering, what the hell does that mean? This book will have answers to your questions. Okay, so the course that I'm pitching at today is at the level of the undergraduates, and our goal for all of GR is to understand this definition of spacetime. Because if we understand this definition, that's all the work done, and from there, all the fun physics that you want to do with GR, black holes, gravitational waves, everything starts the moment we can understand what this means. Okay, have you got anyone else? No. Okay, right. To begin with, today's talk that I'm going to be giving to you focuses on just this word that I've written in red. Okay, so remember guys, I can't hear you, so if you can like hop in and say yes or whether you understand or you don't, that would be really helpful to me because I can't look at Discord at the same time.
Okay, fine.
So today what we're going to do is
Yeah.
just spend our time understanding what a topological manifold is. Okay, and why that's important. And that's our goal for today. And if we start with this, you'll see this structure that we call a topological manifold is key to understanding all of the beauty that you call curved geometry. Everything that you think is different and fun and fascinating with general relativity lies in topological manifolds. Okay, so our starting point for today, okay, is a four-dimensional topological manifold. And out of the words I wrote down on what space-time is, today's goal is to just understand this one key thing. Because if we can understand this, this is about 50% of your GR, conceptual GR techniques right here. Ah, okay, we got Ashmi. Right. So if you want to think about what a manifold is, okay, the starting point is that it's going to be our canvas. Okay, if we're going to work on gravity and we're going to try to understand how we play around with it mathematically, we're going to call this a blank canvas. Just like an artist has drawn it, this is our canvas for gravity. It's the fundamental building block that we're going to use. Okay, so I want to start this lecture off by talking about something that I saw on your Discord chat. And you're going to keep saying that I'm referencing previous talks that you've had because that's the only metric I have to understanding what you're thinking. So I want someone who isn't Pugar to tell me what you spoke about last week on Friday, because I remember I think he had a short course on differential geometry. So someone like Apurva, could you tell me what the word structure means to you?
Structure.
Structure.
Finds out the object is or whatever. It's an abstract concept
Excuse
of
me?
it.
Please excuse me. I couldn't hear anything for a few minutes because my father was calling me. What happened?
Okay. Yeah, we're just starting. So relax, get yourself a notebook and yeah, sit down. Okay, you haven't missed much. Yeah. Okay. That's going to be next Friday. Cool. That's great. Then I get to do my fun bit before, and next Friday could be a revision thing for you. Okay. So the key word that we're going to do is, if you've ever wondered, the question I want to divert, a short discussion I want to have is whether mathematics, right, is it discovered or is it invented?
Invented.
It's invented.
That's what
Yuvraj thinks it's invented. What about you, Pugal? So this is a pretty interesting concept.
It's actually a very
because
confusing thing, right? You don't
Sorry?
know. You don't know whether it's invented or because
don't know if it's discovered. We don't know if it's invented.
no. I
But
could
you
say that
can argue both it's discovered and invented.
No, in a
because you
sense,
can see
yeah, like same thing. You invent it, but it has a life of its own, right? It has its own structure and it has its own mysteries that sort of.
nature follows mathematics, and we like nature follows some rules, and we have represented in mathematical equations, so it can be discovered. Like
Yeah, that's true. That's true, but it's also true that there's a lot of mathematical stuff that physically manifests. Like I think the most popular example of this is something called the Mandelbrot set, which if you Google this particular word, I think it's the most popular example. This thing isn't realized in physics or like any physical world. So the idea is that like mathematics, while it has an interplay with the physical world, Plato spoke about mathematics as having its own universe, which is separate from physics, and it was a huge coincidence, the topic of philosophy itself, to ask why is there this connection between the physical world that we see and the mathematical world. Okay, but for the purposes of our discussion that we're having today, right? For those of you that think there's some interplay between the two, right? The viewpoint that I want to be talking to you is that the bits that we're going to invent in GR, okay, is we're going to say we're going to put 2 and 2 together. We're going to take one concept, one construct, and to that we're going to add another construct, and then we're going to go back and say, well, what consequence does this have mathematically? So we're going to invent something, and we're going to discover if we join two things that are unrelated, what consequences those have. Okay, and that brings me to today's talk on structure. And when I talk about structure, it's something this is a word that should be added to your vocabulary whenever you're doing physics or mathematics. And structure is me taking a particular object and adding more and more things to it, so that it transforms into something that I can use, or it restricts and adds more, as the word suggests, structure to it. So I'll give you an example. Okay, the starting point in all of mathematics, if you're arguing from first principle, is something called a set. Okay, this will always be the starting point of any axiomatic theory in physics, whether it's a set of axioms, whether it's a set of numbers. Whatever you're starting with usually has something defined in terms of a set. Okay, and towards this set, you're going to add something. And whatever you add to this set is what we call structure. So the best example I can give to you is the set of all numbers starting from 0. So 0, 1, 2, 3, 4, 5, dot, dot, dot. Okay, this is my set. So this set, an example of structure that I could add to this, let's talk about various examples. The first set of structure that I can add to this is some sort of ordering, right? Because when I take two numbers, 2 and let's say 5, ordering is some structure that I can add on top of my just these collection of numbers, which helps me distinguish and understand the difference between them. So I could say, well, 2 is less than 5. So these parameters that we have, right? This is all additional structure. It's additional structure that we've added to our initial starting point, which was our set, right? This is clear. This is easy. It's a fairly intuitive subject to understand. Well, the second sort of thing that I can add to my set of numbers is operations to it, right? So I take input from my set and I can give you another output. And this operation that I've added is additional structure that wasn't present if I just had a set, but I start with a set and I add more and more to it. Let's talk about a third thing. If I have a vector space, this should be something new to you. I mean, you've studied these before. So if I have vectors, right? I could just have a collection of vectors. They're just things that point in different directions and have different magnitudes. What structure do you think I can add on top of these random arrows that I have in my abstract space? Rachna, could you think of any structure? Wait, one of you. So if this is my numbers and I've added ordering or operations to it, what do you think I can add to, let's say, a collection of vectors?
A coordinate system.
Sorry, who's answering? I can't hear. Was that Yuvraj? Apurva or Rachna?
It was Rachna.
That's Rachna. Okay. Sorry, I can't hear. So you have to forgive
She
me. I
said
think
coordinate system.
Coordinate systems. Okay, great, excellent. That's a perfect answer. Coordinate systems are structure that we add. Okay, if you guys type in the chat, I can't see it, so forgive me. Okay, coordinates. Anyone else? Any other
Maybe
ideas
a
on what I
plane.
can? Plane.
A plane common to everyone.
Okay, you could have a common plane. A plane. Anything else? Just a structure. Think of, so if I had numbers like 1 and 3, and I added a operation that I call structure. So if I have two vectors, right?
Then we can have a function for the vectors.
You can have a function. What else can I add to it that helps me understand? Just like how I can have 1 into 3, what can I do with two vectors?
Divergence and curl.
Divergence and curl, great.
Gradient.
More, yeah, there you go. More precisely, I can even have a dot product. Right? And the dot product is additional structure. It doesn't exist if I just talk about this space, but I'm taking a space which has whatever I call a vector, and to that I'm equipping whatever I call a dot product, whatever I call a cross product, is just the same as me taking numbers and adding structure to it. So this is what we call structure. Okay. So what we're going to do for a topological manifold, okay, is the same thing. We're going to start with a set, and that's something that I want to talk to you about right now. And why do we even discuss this thing called a manifold? So if our goal at the end of the day is to understand what gravity is, okay, or is to understand how we describe real world objects, this is something new. Okay, this isn't expressed so far in classical physics and all of the stuff that you've mentioned. It's taken for granted, but this is the mathematical heartbeat to all the physics you've done so far. Okay, and the question is this: if I have, let's say, a ball, or let's say a bird that's flying through the skies, okay, what could I say about this bird? Well, we could say this bird in the sky, wherever it is moving continuously, right? It's going to move from there to there. I'm just looking at it. I'm not describing any physics, but it's moving continuously from, let's say, if I'm looking at it, I'm going to draw a coordinate system. This you should now be familiar with because we did this last week as well, this habit of drawing what we call a coordinate system. And we'll see that this bird has moved continuously from 5, 0 to all the way to, there'll actually be 4 coordinates. Okay, there'll be 4 coordinates. I'm going to label whatever, 5, 0 to ... 6, 1. Okay, so it's moved in our world, and we define this movement according to our own coordinate system. Someone else could draw their own coordinate system, right? But what can we say for sure? We can say for sure that this bird, right, has moved continuously. That's the first fundamental assumption that we make, that if you have a bird in the sky, it moves from point A to point B continuously. Or if it stays the same and it doesn't move, it doesn't vanish and then reappear. It always, there's no break, there's no jump where it's going to stop here and then, continue from this place. Is everyone clear with this? The notion of we want, whether I throw a ball up and down, whether we have a bird moving, whether we have a car, whatever physical object that we're defining right now, even if it's standing still, it does not vanish and reappear. It doesn't, there are no sudden jumps. You're not gonna, if you're taking a flight from here to Delhi, you're not gonna suddenly vanish near Hyderabad and reappear near Agra. Yeah.
Like, what if the plane at which the thing going has bumps and curves? Then at a point, like at a certain point of view, you can't see that side, so it disappears out of your center field.
Sorry, there's a lot of noise on your connection.
Okay. Is it fine now?
Yeah, better.
Okay, so like if you consider a car moving in a continuous road, what if the road has some bumps and ups, so that in such a way when it is at the when it goes near the bump where the road dips low, and from the point of view you can't see that. So in that
Leave
like
point
it
of view.
seems to be.
I'm not talking about the point
Okay,
of view at all. I'm just saying the
fine.
physical object does not vanish from here and then reappear. Like there's no gap in my. There might be a gap in the road, but the car might still fall and trace a continuous path. The
Okay,
point
okay.
I'm trying to make is that this bird does not magically disappear from the sky and magically reappear somewhere else. There's no break in its trajectory.
Okay. Fine, fine.
Is this a fair statement to make? All I'm saying is there's no magic in this world. Like objects can't randomly disappear and reappear, 55 feet away.
Yeah.
Does everyone accept this?
Yeah, yes.
Okay. So now the point of asking what a topological manifold is that if we start with a set and we say, well, now I'm talking coordinate system, but we'll go to that later. If I say from here, it's gone from this to this, right? Just a set of points, it's gone from point A to point B, isn't enough for me to say that it's traced a continuous path. That no matter how much I zoom in further and further, like if I look in between this interval, it'll always be a continuous, what do you say, path that it's taken. A set is no longer enough. So the question we're asking ourselves when we do general relativity to start with is what's the structure that guarantees continuity? This is the first, if you're doing gravity from first principles and not doing anything else, the first question we're asking is, what is the structure that guarantees continuity? What is the structure that if I have a curve in the real world, right, if it breaks and reappears, what can I have that makes sure that this doesn't happen? What can I have that ensures there's continuity? And the question we're trying to ask is, what structure can I add to a set of points which satisfies this continuity? And that mathematical construct that we have, which ensures that things are continuous like a canvas and well behaved, is what we call a topological manifold. Okay, so does everyone understand the motivation behind why we're talking about this in the first place? If you end up
To
with some
ensure that we have a continuous structures,
continuous path, that I'm not talking about coordinate systems, I'm not talking about breaks in your coordinate systems, I'm trying to say a bird in the real world, when it's moving from point A to point B, I need a mathematical structure to describe this, one which ensures that there's continuity in its movement.
Okay, fine.
That's a manifold.
Okay.
That's all I'm saying. Okay, this is my assumption, continuity, and I'm asking what is the mathematical structure that allows me to talk about continuity. Okay, so to understand what this manifold is, I'm going to start by talking about a concept known as a topological space. That's our first definition. And that's the first bit of structure that we're going to add to our set. What is a topological space? Remember, if we just talk about it at the courses level, we just only have a set of a collection of 4 points, right? And another set of T2, X2, Y2, Z2, all the way. We just have an infinite connection of points, which just describe if you have a manifold, the bird being here and going from there to there, right? If I discuss this in terms of our world line, this is just some path that we're tracing, and we're requiring that this path is not broken. There's no break. It doesn't, if you're looking at a world line that we discussed when we did special relativity, you can't say that there's a break. Okay, which is to say that if every point here is described by one coordinate, right? There's another point by that one. It translates that this line that you form out of all of them has to be continuous. And for that, we require a manifold. Okay, so we start with, before we can understand what a manifold is, the first thing we're going to do is define what we call a topological space. Okay, and this is the fun bit. Before we get to, so I want to start off with something. Okay, let's start off with a definition. A locally Euclidean space. This is the first fundamental definition that we're going to talk about in GR. Again, the motivation for talking about this is I'll give you the intuition, and then we're going to work through why we're doing this and how we're doing this mathematically. Okay, so you guys have probably understood that the real world space, whenever you have gravity, is curved, right? It's some weird sort of curvature where it's not flat. It's not well defined and flat like we've done before in special relativity. This flat space would have our eta mu nu, which is -1. Remember that? Whenever you have
Yeah.
curvature, it means that the space is badly behaved. No longer do you have straight lines that remain straight. Like if we have a straight line, even if like it's a really weird and distorted geometry. Like the lines look terrible. And this is how it looks regardless of the coordinate system that we choose. Like it's just fundamentally like if you try to stretch it out, you're never going to get, straight lines. And that's what curvature is. And because that's what curved space is, it makes it very difficult for us to essentially compare two vectors. Okay, because anything that we do, if we have a vector like this and we have another vector like pointing here, and we ask, well, how do we add these two, or how would we talk about a resulting vector? The way we do this is we take the tail of this, and we drag this vector here, and we place it like that, right? And then we say the resulting vector is like this. And we do geometry based on this. But the point is that in curved space, all of this breaks down because there's no way that we can fundamentally compare two different vectors. It just doesn't, it's not possible because of the curvature of the space. Okay, like the way that you compare the two vectors is important. So curved space is hell. Okay, if you've worked in GR, curved space really requires you to solve probably 256 equations just to understand this small region of space here. So it's almost impossible to directly try to tackle what curved space is. We need a way to try and understand how this works. And the way that you try and understand how curved space works is a bit of genius. It's really genius, and the person that came up with this, excellent. So the idea behind a locally Euclidean space is that if you have this horribly curved space like this, right? Imagine you're an ant, just a small little ant that's standing on this. Okay, if you're an ant in this horrible space, okay, you don't know what it looks like globally, meaning you don't know what the endpoints look like. You can't see very far away from where you're standing. All you can see close to where you are is this point around you. Okay, and the assumption we're going to start off by making is that wherever you stand in this horrifically curved surface, locally, very, very close to you, okay, the world looks flat. Beautiful, elegant idea. I'll give you another example of such a thing. Okay, imagine you're in a circle. Okay, is this curved? It's definitely a curved surface, right?
Yeah.
I mean, it might be flat in that I can cut one end and then I can like do it this way. But the idea is that as a surface, it's a curved surface. It's not a straight line. Right? This circle that I've drawn here, right? It's a circle. It's curved. So imagine now that I'm an ant that's standing just at the top here. Okay, let's zoom in and let's ask ourselves, what does this ant see? And you'll start to see that if you're the ant, this is what they'd look like first. If you zoom in even more, this is what it would look like. If you zoom in even more, you'll start to see that it more and more resembles a straight line.
So it's
Does
similar
everyone
to how
agree with this?
we feel Earth is flat.
Exactly. Great analogy. So the idea is that wherever you are on this circle, globally it might look like a circle, but locally it resembles a straight line, right? This idea that we're going to use is going to be very powerful, and that's what's going to relate our earlier understanding of special relativity, what is flat space-time is, to general relativity. It's a hugely, to me, it's a beautiful concept. It's so elegant. And the idea is we never look globally, but what we say is all we can speak about are points in a neighborhood around here. Okay, so hopefully you got the intuition for what a locally Euclidean space is. Does anyone have a doubt so far? Speak up now. If there's something that wasn't clear to you, tell me now.
I think nobody has doubt in that part.
Okay, so remember, the starting point is by saying we give up global understanding. I don't care if it's a circle. What I want to do to understand and explain my mathematics is pretend I'm an ant on it. Okay? And the concept is that locally to this ant, it looks like Euclidean space. Now, immediately you should tell me, hey, but Euclidean space? Surely if you're working with relativity, it should not be Euclidean, right? Surely it should be Lorentzian. Like locally, it should be that eta mu nu, the Minkowski space that we spoke about. And the answer is yes. Yes, we're going to require that it's locally similar to what's called Minkowski space. But to first understand the concepts that we're talking about, we're going to start by understanding Euclidean space. Because a lot of the concepts that we'll work with in Euclidean space have a direct carryover to a locally Minkowski space. Is this clear to everyone? So this is just like a small baby example where before we require that it it follows special relativity. To understand what a manifold is, we're just going to work with locally Euclidean. Okay?
Okay.
Is this clear to everyone? Okay, here we go. Here's my definition. I think you should write this down because we're going to talk about what this means. A locally Euclidean space. Locally Euclidean space. We're going to write it as M of dimension D. Is a topological space for which every point P, which is in my space, has a neighborhood. And here's the key word now. I'm going to write it in green because it's something that we need to understand. If you don't understand what neighborhood is, that's fine. We're going to get to it. Here's a good word. Whenever we do differential geometry, you're going to hear this again and again. Homeomorphic to an open subset. U, which is a subset of R, D. Okay. Does everyone see what I've written down? A locally Euclidean space M of dimension D is a topological space. I haven't defined what that is yet, for which every point P has a neighborhood which is homeomorphic to an open subset U, which is an element of RD. Lot of words. Let's explain what this means. Before we get to what this is, I'm going to tell you that it all hinges around what an open subset is. Okay, so just from what you know, Apurva, could you tell me what an open subset is? In general, don't think GR, don't think geometry, but just do you have an understanding of what an open set is?
Subsets are like parts of, we select some numbers from the set and then make it a subset.
Okay, subset is if you have a giant set, the subset is just a tiny part of it. Okay, so this is a subset. What does the word open mean?
We are open to select any set of numbers, maybe.
Not quite. Does anyone else know what the word open means? I mean, when I tell you this, definitely be like, shit, we've done this in 6th standard. But does anyone know what the
You
word
can
open means?
even select the first and the last.
Yeah, there you go.
Close.
Yeah, so the word is open and closed. So open just means if I have, this was the symbol.
Consider the starting and the ending elements of the set.
Yeah, exactly. So a closed subset is just an interval that has this symbol here, which says that 1 is included. This means it's open, which means this includes everything up till 2.999999999. It does not include the value 3. Right? That's the word. That's what the word open is. So I'm going to show you how this word open, okay, ties into what I had earlier told you about my ant in our Euclidean space. And you're going to immediately see why this is such a beautiful definition. And this is what I love about mathematics, just smart thinking. Okay, so here we go. Here's what an open set is. And this is the first example I could find on Wikipedia. Okay, and so we're learning topology at the moment. Okay, an open set in topology is the generalization of what this open line interval is, which is that if I have my number line here and I say, well, what I'm going to do is I'm going to talk about all the points in between here, and I don't include the endpoints. Yeah, or let's say I can even have one set of this, and yeah, so everything here except this, meaning from 0 to 3 up till 3. So everything up till about 2.999, right? That was our earlier example. That's what our open set is. Now there's a beautiful topological geometric understanding of what an open set is. And the example to understand is just consider a circle of this kind. Yeah, that's my circle. I'm going to do a terrible job of coloring this. Okay, so that's my, so I've drawn two different things. Okay, so you can see my blue circle, that's the outer circle, and you can see my red circle. Shit. You can see my red circle. Yeah. Right? The blue circle is called the boundary set. Right, this is blue. And the red circle is called the open set. So now just see how this concept of an open line interval has a beautiful geometric meaning. Okay, so what this is that if I talk, what's the equation of a circle? Could anyone tell me?
X squared plus y squared is equal to r squared.
Okay, so here, if I had to draw my blue circle, right, my blue circle is just here. X squared plus y squared is r squared. So this circle is comprising of x and y equals r squared, whatever. X squared plus y squared equals r squared. This is my fundamental equation for this larger boundary circle here, right? So whatever this value of r is what defines the large outer circle, right? So now can you all agree that my open set, okay, is all the circles, every single circle that's inside this this blue one. So for example, I can draw a circle like this, I can draw a circle like this, a circle like this, I can draw a circle. Does everyone agree?
Yes.
Okay, so guess what this says? It says that the open set that I spoke about now is a set of all circles lesser than
r.
Then
Beautiful. So this is my same exact interval that I had in my real number line, right? But what does it do? It says I'm just going to look at all the collection of all of my circles which are less than this arbitrary r square value that I have. Does everyone agree? This is a beautiful geometric interpretation of what an open set is, right? So now we go back to my definition of what that a locally Euclidean space is. And remember, this is what I'm saying. If you're an ant on top of a circle, to you, what looks like a straight line. So now what I've said is that is a topological space for which every point, let's say if I draw this, and I pick a point here, is a topological space for which every point P, so this could be P, this could be P, which is a subset of, which belongs to M, so this is my M, has a neighborhood homeomorphic to an open set. So what is, do you know what the word homeomorphic is? It's a technical word in maths and in topology. I don't think many of you, this would have been the first time you're seeing it, okay? So whenever you see the word homeomorphic, you can immediately think of it being equal to. It's the topological way of saying two shapes are the same. Okay, and what this essentially means is there's a set of conditions for something to be homeomorphic. It says that every point, I'll explain what I'm trying to say first, but let's say this is my blue, and this is my red. My statement that I'm trying to say is that any point in my topological space that I have here, okay, is the same as an open set, okay, for sorry, every point that I have here has a neighborhood meaning all the points that are around it, right? Can everyone agree that this circle that I've drawn in blue, okay, it's arbitrary. I don't know how big or small this circle is. I can even draw a smaller circle if that pleases everyone. But I've said that every point in the neighborhood of my point here, so that would be here, right? And what I've said is all these points that are in the neighborhood of P, okay, are the same as this, an open set, because I'm not including the boundary next to my point. I'm including all the points that are around here. Does everyone agree?
Yeah, but how do you define that boundary? Like, till which area that everything remains homeomorphic?
It's arbitrary. So if you're doing calculus, you could say, well, the boundary is defined as x plus some small epsilon in all directions. So it would be a circle of radius x squared plus y squared lesser than whatever, x plus epsilon, whatever. You get what I'm trying to say. It's you can define it to be arbitrarily small. It's not the distance that you take is not particularly significant. It has to be arbitrarily close. Okay.
Oh, fine.
But the point of me saying this, the beauty of this is it allows us to talk about the nearness of a point. Like another point, let's say P dash, right? It allows me to talk about whether these 2 points are nearby or close by without me ever talking about the notion of distance. Can everyone see this?
Mm-hmm.
Isn't this brilliant? It tells me that any point that I have in its neighborhood, which is, you can think of it as a tiny circle, is the same as this open subset that we spoke about right now. And it tells us if any point P has another point in its neighborhood, then it's both of these are a part of this locally Euclidean space. Okay, does everyone get this? And here in differential geometry is how we talk about it. So let me just get to that. Is everyone clear? Does anyone have doubts?
Like, so it is like assuming a new guy who is joining a group of students to have similar characteristics similar to them. Maybe.
Yeah, but very, very close. We're talking about points in the neighborhood. So it's like me saying if I'm an ant on a circle, I'm saying another ant very close to me. We both see the same straight line. Yeah.
Oh, okay. Fine.
It's important that we talk about the open subset. That's what I meant by neighborhood, and that's what I mean by homeomorphic. Does everyone agree with these 3 words? Okay.
Yeah.
So now, if I had some sort of like a large space, which is, I told you, globally horrendous. Okay, it's globally horrendous. Locally, it might look better. Locally, it might look like this. Let's pick a point here, and this is my neighborhood around it. Okay, here's what we do. How we do physics, okay, is we take this neighborhood point and we say how we can do physics is locally, we will construct a Cartesian coordinate system. Whatever you like beautiful, lovely physics will be done on this Cartesian coordinate system. How does this look? Well, according to us, when we chart it, it might look like this. Yeah, whatever this was in real life. Think about it this way. If I send you, here's what we're doing so far. Okay, what we're taking is you go to Paris, and in Paris, look at the Eiffel Tower and draw it. You might draw it, for example, this way. This is a terrible drawing, right? Your friend might actually draw it sideways, saying that, well, this is the way I want to look at it, right? So there's a real world, and in the real world, the way that we do physics is that we chart it to something that we know. We call it a coordinate system, and we describe that same object in our coordinate system. Is everyone clear with this?
Yeah.
Okay, so guess what we do? We say that the real world, okay, we're going to chart every point. We're going to take every point that we see here and map it via some map, okay? And guess how we go back from this chart to this real world? Phi inverse. You guys remember our Lorentz transformation, what we said a matrix was? A matrix is something that transforms coordinate systems. If we go somewhere, that's me rotating to the friend on the ceiling. The inverse is me coming back from the ceiling back down.
Yeah.
Okay, so that's what this is. So this phi is what we spoke about earlier. It's called the homeomorphism. Is this getting technical for you guys? Because we're going to get to what we're talking about fairly soon. Okay. So the idea is, if I'm looking at the real world and I say in my coordinate system, what is this point here? Let me call this Q. What is Q in my artificially constructed chart? Well, this would just be phi, which is our map, and you plug in, sorry, it's not J, it's Q. Right? This is what I'm doing. I'm taking my map, and into that map, I'm plugging my original coordinate, and that spits out the image that I'm going to see. I hope no one's confused about why we're studying this. We're studying this because this is the structure we need to understand how continuity works.
Mm-hmm.
Okay, so what we call this phi, okay, this phi that we have is if we have some chart that we say here, whose neighborhood around that point is very similar to something that we can talk about in RD. Here I've drawn R2, right? That's what we call a locally Euclidean space. It's something that we have some kind of coordinate system that we can describe only the points around this. I can't do the whole map and take it here. I can only talk about the points in that neighborhood is this. Okay. Now imagine something. Okay. So remember, so what I've written right now. Okay. This is our coordinate map. This phi here is called our coordinate map. And trust me, you want to be learning this stuff because if you're doing general relativity, this is differential geometry. This is the 101 that we're going to be doing, and they're going to do a lot of this when we get to GR. Okay, so I'm just going to give you a quick example of what we're talking about so far, locally Euclidean space. Okay, circle. There's my circle. Yeah, there's my circle. Okay, this is my circle, and what I'm going to do, remember, I can't pick the whole circle. I need to pick an interval that an ant sees. So I'm going to say I'm going to pick from here to here. Okay, this interval. So everything here. What I can do is I can map this via phi. Okay, to a straight line. Can everyone agree that this can be mapped to a straight line? I take this point and I say it goes there. I take this point and I say it goes there. I take this point and I say it goes there. Does everyone agree?
Yeah.
So that's how this works. The key point I'm trying to make right now is that when we do GR, you can't cover the whole circle with one map. Remember, I said globally, it can't look, what do you say, like a circle. Locally, it'll look Euclidean. Okay, but we're going to reach a point in this circle that becomes a problem. So if I start with an interval here, okay, this, I can chart all of it, chart all of this, and say, well, this is a locally, I have some map that takes it to some two-dimensional, it can look like that. Except when I come back to my same starting point, meaning my chart that I've drawn, a coordinate system from one to the other, will work from 0 till just less than 2 pi. Okay, but when 2 pi and 0 are the same, it no longer is an open set. It becomes a closed set. It's equivalent to me now in our open set line. We've taken our radius all the way till here, and it's no longer an open set, which means it doesn't work. Okay, so what we have, or what we do when we have such a structure, is that we take multiple charts to cover the same object. And the way we do this is that if we have a circle like this, one chart will cover from here to here this way, and maybe another chart will cover here to here, or like, yeah, everywhere except this one point, like that. So if you have two charts, you have two charts that cover the whole surface, and now you can talk about it. And the equivalent of this thing is if I had my neighborhood here, what if I had another point, let's say here, and the other point had a neighborhood like this? Can you see that there's an overlap? Let me draw this better. By the way, is anyone confused at this point? This is a lot of new jargon. It's important because we need to study this, and I'm going to give you a definition soon. So far, the only thing we've defined is that any weird, horrendous structure that we have, I require that at every point, I can have a neighborhood around that point which is well behaved. Just something that I know what to do with, and the something I know what to do with is draw a map, which to me looks nice and well behaved with a Cartesian coordinate system.
So what you're telling is that if you map a circle in a Cartesian coordinate like a straight line, and after the 2 pi, what happens is that it breaks and again starts.
I'll get to that. I'll get to that. I'll give you that example better. Okay, so you see this. Can you see that this is one example of? I'm saying that any point that I have has an open subset in its neighborhood, and that open subset looks locally Euclidean. Yeah. And the way we're going to do this in GR is we're often going to study the same object from various coordinate systems. So take a look at this. I can have another point here. Okay. Let me draw that in green now. I have another point here. And it's, there we go. Can you see this now? So this is the entire point that's in its neighborhood. But can you guys see that there's an overlap?
Yeah.
There's an overlap in this region in red. Okay. Here's what we're going to get to. We're going to say, how do I do this green structure? Well, this will have another map. Give me your favorite symbol. I'll say chi. And another one, chi inverse. and it'll lead to another locally Euclidean surface like this, where it might look like that. And you'll have the bit of it that's overlapped like this to the other person and the other chart that we've drawn. Maybe the overlap region will be here, right? So now look, I can describe this region of overlap either through this map or through this map. Okay. And what we're going to require is not the entire map, but just the region that's overlap, right? I should be able to describe it both by this initial map here as well as this chi here. So I need a way to go back and forth between the two. And if you understand this following picture, this is what differential geometry is. And I'm going to move from this back to a manifold. Okay, because I think this is a concept that I'd like to develop over time. I think it might be a lot to take in one session. So I'm going to move to begin GR and just say, like, we're going to take this for granted, but I wanted to show you where this comes from. So I'm just going to draw one final picture. Okay, and I'm going to say that this thing that we have here is what we observed. Okay, this is our coordinate system. This is our chart that we draw, and this is how we do all of physics. Everything that you've drawn so far, like a line or a vector or anything that we've done with geometry, okay, is what we perceive. And it could be different. It could be different, whereas someone else could have their own coordinate. Your friend could be drawing this. Or another way to say this is, the intuitive explanation for this is you've both gone to, let's say, Agra, and you're both drawing a picture of the Taj Mahal on your books. And one of you could have drawn it like this. Your friend may have drawn it like this way. Okay, or let me give you a better example. Your friend draws the turrets and the entire structure. And what's the bit that's in common? Here, this building is the bit that's in common between the two diagrams, which means if we're talking about continuity in the real world, there should be a way for you to compare what you've drawn here to what your friend has drawn. Something similar to what we had with the Lorentz transformation. And what that is essentially is the structure that defines what continuity is. And the question I'm asking is, how do I go from this shaded region and understand what that is to this shaded region and understand what this is? So this is where drawings, whenever you're doing general relativity, become extremely important. So take a look. Okay, so if I'm talking about this point here in my here, let's call that point X, right? I want to say me who have drawn about when I've drawn this local chart in my book like this point of overlap. How does it look to a friend? How does X look in here? What I'm going to do is trace X back to here and then translate that this way. Does everyone agree?
Could you just repeat it again?
Okay, so let me just show you where all these maps are going, because this is curvature. You asked for GR. This is what we're going to do. So this is my I call this U, which is my open subset, which is a part of my larger topological space. This is my neighborhood. Okay, my neighborhood has a point that has an overlap here. What does my map do? My map is a function phi, which is a map from U to R. Meaning it's some real world object, which is the Taj Mahal, and it maps every point on the Taj Mahal to coordinates, which could be 6, 0. The tip of the Taj Mahal could be at 7, 2. And that's what this map has done. It's taken every real world coordinate and translated it to my book and has told me, when I plotted it out in my geometric chart, where this picture of the Taj Mahal is. Okay. This chi is another map which takes that same subset, or in our purposes, the crossover, the union between these two. So I call this U2 intersection U1. Okay. And what this is also just the point of overlap. And what I've done is I've drawn another map from this to RD, which is me saying, oh, well, if this is the Taj Mahal that I see, well, the tip that I call the tip here corresponds to 7, 2. And that's all this map says. The way you do this is you say, well, the tip of the Taj Mahal is 7, 2. Is it clear?
Yeah.
So now the question I'm asking is, I described the tip of the Taj Mahal to be 7, 2. Let me give you colors because colors help. So in one chart, we call it 7, 2. And in the other chart, the green chart, we say 3, 4. How do I know that I'm actually talking about the same thing? And because we're talking about the same object, I should be able to describe it in both of our coordinate systems, like both ways. So I need a map that goes from my locally Euclidean space to my friend's locally Euclidean space, provided when does this work? This only works when you have a region of overlap. It does not work if your friend is mapping a different part of the world and you're mapping a different part of the world. Then there's no overlap and no point for you to compare. This only works when you have a point of overlap. Which is to say that if you're an ant on a circle, you and your friend can only talk if you have an ant and there's another ant. You can only talk if you're significantly close together. That's essentially, Yuvraj, you'd asked me the question on what do we mean by neighborhood. This is exactly what we're saying. Okay, so do you guys see the question I'm asking right now? Like, I need a map that goes from here to here, a map which goes from 7, 2 to 3, 4. And the answer is pretty simple right now. The answer is just to say, well, if phi is my map, what I'm first going to do is feed 7, 2. So let me take it this way. I'm first going to feed 7, 2 into phi inverse. Does everyone agree? If phi is the map that takes me from my manifold to my locally Euclidean space, phi inverse is what takes me from my locally Euclidean space back to the manifold. It's not a manifold, it's a topological space, right? Does everyone agree? That's what I'm doing. All I'm doing is going from the neighborhood to open subset, and then I'm going back from, that's my inverse. So if I had to find what 3, 4 is, how do I compare the two? First, I'm going to go back to my manifold and then go down via chi. So does everyone agree? My first thing to do is to go back using phi inverse. And then to that, I'm just going to act with it on chi. Does everyone see what I've done here? All I've done is go backwards from my point of view to the real world and then ask. So I've asked what is what I call 7, 2, which is the tip of the Taj Mahal. What is that in the real world? And then what is my friend C, which is the map chi? Does everyone agree with this? Is anyone confused? If you are, like, tell me, because this is quite a confusing talk, but we're done. We're done with this. Is the main thing that I want to do, and then move on to GR from here. Is anyone confused?
But in this, we see that our transformation is possible only for a particular small region. Like,
Yeah.
so we can't consider a wider area.
No, we can't. Remember that. So we start off by saying we give up global understanding.
Okay.
Oh, this only works, but now we're going to have fun. I'm going to tell you why this key concept, if you just understand, I'm going to explain how we understand the globe, essentially. But do you guys understand this kuti thing? That if I was going to the Taj Mahal in real life, with this Taj Mahal, I'm drawing a picture of the one particular part of the Taj Mahal. Let's say the tip, and that's my drawing in blue. Okay, I have a friend who's very close to me in the Taj Mahal is drawing something that's the tip, but something close to the tip as well. So there's a bit of an overlap between my map and my friend's map. I've now asked for a map that takes me from my coordinate system to my friend's coordinate system, which is this chi after phi inverse. And what does that mean? That just means I'm asking from, well, this point of overlap here, okay, x, I'm taking it back to the real world here. And then from there, I'm just dropping it straight down to this. And that's the same as me going directly. And how do I go directly? Well, it's chi after phi inverse. Does everyone agree?
Yeah.
Okay.
Yeah.
So now here's the key definition. So if you've understood this, like all we've done is transform between a change of coordinates, right? Does everyone agree? Like the real world does not care about what we've done. Whether we call it the tip of the Taj Mahal, whatever we say it is, it's always going to exist. The bird is always going to exist. The real world is always going to exist. Everything that we do in physics comes down to choosing coordinates, and that's exactly what I've drawn for you. You've chosen coordinates by representing the real world in your book, which is in blue, or your friend's book, which is in green. And all I've asked is that we have a way to compare blue and green. And the way to compare blue and green is to take your point and feed it back and say, where did this point come from the real world, which is phi inverse. Phi inverse is the opposite map from your book to the real world. And then say, okay, the point in the real world is the door to the Taj Mahal. And then you'll say, what is my friend? How does my friend draw the door? You take the map, chi, and the point, which is the door, and you get what your friend has drawn.
But even real world is a point of view, right? It's a different point of view from.
Exactly. So the point that, so from your frame of reference, what you call the door is chi times the point that you're looking at. And what I call the door would be phi times the point that I'm looking at. So the real world is untouched. All the physics that we're doing has to be on this sub open set that I'm talking about.
But
You've
is there a
said
way
exactly
to,
what I'm trying to do. Sorry?
like, is there a way to actually find out that the phi inverse that we have found is actually the real coordinates of the real
Hey,
world?
your voice is breaking up.
Is it kind of?
No.
Okay. Am I audible now?
No.
Fine, let me type for.
Sure.
Your voice is distorted a lot, actually.
See, this, I don't expect all of you to understand this on your first day. The idea that I'm trying to say is the way we're going to describe the big world is to break it up into small bits like this, understand how they look, understand the overlap, and I can even draw a third map here. So my third map could be a friend here with another overlap point here. One sec. It's syncing. So this happens every time I try to draw. It should work in a second. Yeah, you can see what you can see what I've drawn. Could someone read out Yuvraj's question, please?
Yeah.
Okay, but do you understand how all I've done is I've taken a point. I've said there's a neighborhood around that point, and every point in that neighborhood looks locally flat, which is my Euclidean space here that I've charted. Okay, I've not done real physics. I'm
Yuvraj
arguing to
asks,
you.
how do
Sorry?
you find the phi inverse is the actual point in the M in the matrix?
Because you've chosen 5. This is okay. So technically, this falls under the definition of what a homeomorphism is.
Finally, transformation is correct. That's this.
But phi is something that we define. It's as simple as this. It's saying that if I take the, let's say, I could give you an example. Let's say if I have, let me look for an example. Hang on. I could say, for example, a circle here. Here we go. Here's a circle. I'll say I'm taking this particular neighborhood, okay, whatever that is. And I'm going to say my map phi is cos inverse theta from here to here. What would phi be? What would phi inverse be? Well, it would be cos inverse theta, right? Within this interval, right? I need to check if my trigonometry functions are well defined within the interval I've chosen, but that's the idea. A map is just me taking a point and going from that point to what we call. So immediately, this is the example that I showed you earlier of, well, having a circle and going to a straight line, right? I can map it to a straight line by taking the cosine of the values between here and here, and that'll just give me an open interval between here. And the map phi I choose is cos theta. Does this make sense? This is a very simple baby example, and the way to go back would be the phi inverse, where you take the point here and you feed that in. Yeah. So the question I'm asking is the same. There's another interval here. What if you had someone who defines chi to be sine theta? And then, chi inverse is sine inverse theta. How would you go from your coordinate, your line here, to your friend's line? Well, you'd first follow phi inverse to that point here, which would lead you back onto the circle, and then you'd take that line down to your friend, and you'd apply chi to your point. Is this clearer to you now? I mean, I might have chosen a poor example because I haven't thought about it enough to understand whether sine inverse is defined within the intervals I've chosen, but this is the general idea.
The thing which I wanted to ask was that how do you find out that the transform was actually a sine theta or actually in cos theta?
That's your choice. This is your choice. You get to choose what map you're doing. Just like how if you're drawing an image of the Taj Mahal, you get to choose which color you draw it from, how big is it, how small is it, what portion of the Taj Mahal you're drawing. That's your choice. So phi is your choice. It's your choice how you're going to define it because that's your frame of reference.
Fine.
Okay. All I want to know and all I care about is for this physics to be important, I just need a way to transform between your drawing and someone else's drawing. And if I can move on now, you'll understand immediately what we're going to say.
Yeah.
Okay. Let me start by saying differentiable structures.
In all these points, we take the smallest part, like smallest surrounding over near us, and we describe it as the like Minkowski space. What if the space-time is so curved that we can't even have a flat that's like we can't
Then it's not a manifold. Simple. Then it's not a manifold. Then you can throw it out and say general relativity does not care about it. I'll give you an example. Okay, so I'll give you an example. I'm not even defined what a manifold is yet right now. All I've told you is that the key principle, the beautiful mathematical idea is that whatever we're looking at, if you zoom in and you pretend you're an ant in the surface, it's locally flat, locally Euclidean. That's all I've said. And the bit of math that I've drawn here is to show you can transform between one to the other. Okay. Now, we were talking about continuity. I'm moving forward with that. We can come back to this if there are bits that you don't understand. But all I want to tell you is that essentially our coordinate system is us taking a point in the real world, drawing it in our notebooks. So if you were to draw a house or a scale of your own house, like think about it this way. If I was to tell you, Apurva, go home and draw your room in your notebook. Way to describe your foot of the bed is, so remember the language that you're talking. What do you call the foot of the bed? You call the foot of the bed 7,2. It's a coordinate in your notebook. You said the foot, it's like you saying, hey, Rachna, how have you drawn 7,2? And Rachna's like, what? Your 7,2 is going to be different from my 7,2. 7,2 in my book is a pillow. 7,2 in your book is a bed. So your language breaks down. So what you're going to see is, wait, what I've called 7,2 is the foot of the bed. And how do you do it? You take the phi inverse, which is essentially that. It's a coordinate map, right? And then now you're looking at the real world. And so you've said, okay, 7,2 in my book corresponds to the foot of the bed. Now you can talk to your friend and say, okay, foot of the bed, what do you call? And she'll say, wait, she'll do her coordinate transformation, which is applying foot of the bed, chi. Chi is the map. So chi and plug in foot of the bed and you get her coordinate system, which is 3,4. Does this make sense?
Okay, so yeah, identifying what we are describing is the real world. And then,
yeah, but not based on what you've drawn in your book, but what the real world actually is. So that's important to make. There's a distinction. So let me just get to this. Okay, the point I'm going to make now is that not all maps are allowed. Okay, not all maps are allowed. Let me explain to you now. So this map from this open subset that I had here, the collection, this is your room. Okay, and I go via phi to your drawing of your room in your book. Okay, this thing is called a chart. And soon you'll understand why I've called it a chart. Okay, so the first thing that we're going to say is this, a differentiable structure. Of class, I'll explain what this means. Okay, this is I'm going to move on quickly to GR now after this. Okay, does everyone see what I've written? I've written that a differentiable structure. So now imagine, so remember, we started off by saying we just have a set of coordinates. Okay, our real world, the first assumption is to say that our real world, we're interested in small subsections of the real world. So if you're looking at Earth, you're not going to be able to cover Earth. Apurva is only looking at a small subsection of the Earth, which is Adyar. That's all she can see. She can't see the whole of the Earth. All she can see is Adyar. Okay, and how she looks at Adyar is she looks all around her at the real world and then draws a map. That's exactly what it is. A map in her notebook of what she thinks Adyar looks like. Okay, someone else draws their own map of what Adyar looks like. They might draw T-Nagar. Okay, so that's all this is right now. Okay, it's a collection of charts. So what we're going to do is all of us that are currently listening right now, we're going to go out and draw the bits of Chennai or bits of India or bits of the world that we're near, right? And that's our collection of charts. So Apurva sees Adyar or wherever she lives all around her. You see T Nagar. Someone else takes a map in Nagambakam. And all we've done is information gathering so far. Okay. And now comes the first criteria to identifying the structure that gives us continuity. The first one, the first criteria is that every point is hit. Okay. At least once. This is crucial. Does everyone see what this means? It means that this was the question that Apurva was asking, that how do we understand it globally? We don't. We have local charts that only cover Adyar or whatever. But globally, we have so many charts, millions and millions and millions, such that we cover the whole of the Earth. Is this clear to everyone?
Yeah, yeah.
Okay, so now guess what? So the next thing that we're going to see is, remember the transition map. This is from me going from Apurva's drawing, and she's going to now translate what Rachna did. So this should now be fairly clear to you. This is just saying whatever Rachna drew, I'm going backwards to see what that looks like in the real world. And then I'm applying Apurva's map to understand how Apurva sees it. This is Apurva and Rachna translating and talking to each other. Okay, what we're going to see is this map from Apurva to Rachna. We're going to throw out all maps except those maps that are differentiable. And how many times differentiable? Well, you need at least twice. Okay, but in reality, for general relativity, we're going to assume that it's infinitely differentiable. This map that Apurva has drawn, the map that Rachna has drawn, the transition map between one to the other has to be infinitely differentiable. And this immediately you can appreciate that if I had a map that I'm drawing of Adyar, right, and someone else is drawing a map of T Nagar, we're going to throw away every other map except the maps that themselves are differentiable. And going back to the significance of this is that when you look at this thing here, this is the crucial idea that ensures that the regions of overlap, right, this map is what's continuous. This is the crucial structure that enables us to understand what a manifold is. Okay. The other assumption we're going to say is that this collection of charts that we have, we can't add any more charts. So you've just done all the work there is. You've collected 5 billion maps. There's not any more that you can add. Okay. So guess what a collection of charts is called? It's called an atlas. So now, once I've written this down, I think one more word in our initial definition should now become clear. A smooth atlas. Right? So that's what we've done. And I'll explain what this is. So I'm just going to draw another quick picture for you, and then we're going to move on to starting, because this is a mathematical introduction, and we're going to move on to a little more physical stuff. So this is my first neighborhood, okay, and this is my second neighborhood. Remember, here you can see that there's a point of overlap. How does this look? Well, this one has its own map phi. This is Apurva's drawing, and this looks in Euclidean space something like that. The point of overlap is here. You can have another chart, call it that, and that has its own coordinate system where this circle may look like this. And here's the point of overlap. And what we require is this map going from here to here is differentiable. This is what we require. Okay. So a manifold essentially is a locally Euclidean space, which is also equipped with these differentiable maps. That's it. That's our mathematical understanding of what a manifold is. Okay, is everyone clear? We can remember this. If you're confused about something, don't feel like it's something you need to learn immediately. This is a This is a crucial concept, but this is the basics to what differential geometry is. Where any physics that we do, we're going to do it by picking a map that's convenient to us, and then doing some physics in this local coordinate system, and then understanding that we can transform to another coordinate system. And once we've looked at that bit of object in one coordinate system, we ask, can we describe it in another coordinate system here? And if the answer is yes, you can, then everything that you've made, your predictions that you've made, are true predictions because they don't depend on a choice of coordinates. Okay, does everyone understand why we picked this and what we're trying to do? So let me give an example of something that isn't a manifold and something we can throw away. Okay, so a circle is a manifold. Okay, but something like a circle, you can't cover with one chart. Remember, the chart is this thing here, this blue line equipped with a map. Okay, the circle is not something you can cover with one chart because when you get to the point 0 and 2 pi, it becomes a closed set. So for a circle, you'd want one chart to cover everything except this one point, and another chart which covers everything, and then together, chart 1 plus chart 2 forms an atlas, and you've got yourself a manifold. If you can prove that the maps that you've drawn for these two are differentiable, and that's your choice to make. Okay, an example of something that isn't a manifold is the figure 8. This is not a Mobius strip, that's different, but the figure 8, if you zoom in at that center point, right, this does not have a locally Euclidean space. There's no point around this region where you can form an open subset because of that crossover. So the simple way, you can read up about this. I'm just giving you a simple example. I've not proved why it is or why it isn't, but an example like this does not have a locally Euclidean space there, so it isn't a manifold. You can throw it out of the window. Okay, so circle, great manifold. If you have a sphere, it's a manifold. So do you already start to see that if we're looking at relativity, and we start off by saying that it's a 4-dimensional topological manifold, you see it's already thrown out certain structures that we just can't work with. It allows some things, but it disallows others. Okay, so do you see how immediately you can now start to see, okay, the smooth atlas, there's something to it. And yeah, we're trying to constrain what this canvas is. Is everyone clear? Does anyone have questions? Because now we can start GR. This, you probably won't require this unless you're doing actual research work with different maps. You'll never have to do this unless you're properly doing mathematical differential geometry. I just thought you may want to learn where a manifold comes from. So for the purposes of our course, I don't care what a manifold is. Okay, so we're going to for our starting point. Now we can start with GR. So 1.1, manifolds. A manifold is just something that's a blank canvas. And to this manifold, just like I told you so far, we're going to add structure to this. We're going to add structure to this manifold until we can call it spacetime. So now immediately from our introduction, you should understand that whatever this structure is has to do something with atlases. It has something to do with orientation. It has something to do with the connection, which is torsion-free, right? You can start to see that we're adding some things to this, to a manifold, and we're going to call it spacetime. Is everyone clear?
Yeah.
So coordinates. Coordinates are labels that we use to denote the position of points in the manifold. In a 4-dimensional manifold, we require 4 coordinates to label a specific point. And now you should see this is why we did special relativity, because we understand that this has something to do with our 4 vector. And if you think special relativity, you should now remember that we want this quantity to be invariant. So whatever we do with these coordinates, A, the physics shouldn't depend on them, but B, it should be invariant, and the length of this vector that we form out of them should be invariant, right? So the idea is that whatever we do in these coordinate systems, okay, you can even write it as t and radius theta. You can do it in different coordinate systems, and the goal is that whatever you do, you should be able to redo a derivation using a separate set of coordinates, and it should come true. You should get the same result. And that's essentially what I've done, is tell you that I can do a derivation in this map in this coordinate system, or I can do a derivation in this map in this coordinate system, and there should be a way to transform between the two. this that I've just told you right now is the principle of general covariance. That's the starting point for general relativity. Okay? Are there any doubts so far?
No.
No.
Curve. A curve is a one-dimensional object inside a manifold. So if you remember this to be a manifold, whatever that is, a curve is just a point. Okay? And this curve, how do you describe it as? Well, you describe it by 4 coordinates, right, at every point. At every point, it has 4 coordinates that describe the curve, right? So how do I parameterize this curve? Meaning I need a slider that if I slide from this point to all the way like that to this point, every time I slide my slider, I should get return 4 values of x, y, z, and t. And so I say it's parameterized by lambda. And all that tells me is for a particular value of lambda, let's say lambda 1, it gives me this point. Lambda 2, this point. Lambda 3 to be here, right? Is everyone clear with this?
Yeah.
Okay. So this is what this is. So this is what we call a curve. And what I'm going to tell you now is, if you remember our invariant interval, S. Actually, I'll get back to this in a bit. Okay, so you remember what a curve is. It's a curve that's parameterized by this. Okay? The next thing that we want to start defining, and hopefully now you'll understand why I spent so long trying to explain what a manifold is we're now going to get to what's called a tangent vector. So if you guys remember covariant and contravariant vectors from when we did special relativity, this is where it comes into play. Okay, so our manifold that we have up here, okay, a manifold which is like this. Okay, if there's a curve, this might be a, remember, it's a ugly, every time you see general relativity and you're given a space, the starting point is to assume that it's horrendous. And it's horrendous and ugly and we don't know how to work with it. So do you guys remember what was the key crucial idea in the last hour that we developed? The idea was that locally it should look clean. It should look Euclidean. It should look something that we can work with. If you're an ant, locally it looks flat, right? Guys?
So, yeah, so like any point in the curve, you find the equation of tangent kind of thing.
Exactly. So what we're going to do is, Apurva, are you following? Purval, are you following?
Yes, yes. Yeah.
So what we're going to say is that every point on this curve, which is parameterized by lambda, okay, on so a point P on a curve C in our manifold M, okay, we're going to define a tangent vector T. And this tangent vector is defined as this. We're going to define T as the limit when d lambda tends to 0. Does everyone understand what this limit is? What is what do you think x plus lambda plus d lambda is? Remember, if our curve is here, okay, so if I'm drawing my curve, okay, this point is given to me by x mu parameterized by lambda. So the point immediately next to it is going to be x mu lambda plus delta. Okay, so how do we do calculus? We do calculus by saying we're looking at changes. We're looking at changes in the limit where this d lambda goes to 0, which means we're looking at the immediate vicinity. As you'd asked, how do we define a neighborhood? This is the definition. Does everyone agree? And what we're going to say is that the tangent vector is ds with delta. Okay. So what is this? This first bit, if you're wondering why I've used a strange delta symbol, that's the definition of a derivative. Okay, so we're just going to write this as a total derivative where, given that the parameter only depends on lambda, this is how we write it. So a tangent vector is the derivative of s with respect to lambda. What is s? S is an infinitesimal separation vector, okay, between the point P and some nearby point. This is what we had said, P and another point P dash, which is parameterized by lambda plus del lambda. So it's essentially just telling us the distance, or what we call the separation vector, between this and this. That's what S is. So let me just draw that. I'm just going to blow it up for you. So assume this is x mu of lambda, this is x mu of lambda plus d lambda, and this vector that we had out of our curve is what we call our separation vector. Is this clear to everyone?
Yeah.
Okay, so now the crucial point to note is this tangent vector t only touches the manifold at point P. You can't drag this t all the way here and say it connects here at all. You can't, okay? It only touches the manifold at the point P. And understand something here. Have I defined any coordinate system so far on my manifold? Do you see any coordinate systems?
No.
So the t that I've chosen so far is independent of my choice of coordinate system. So all of the physics that I'm doing right now is independent of how I choose my coordinate system. Okay, so let me just give you a quick example, because your tangent vectors that you do is something that you're going to be calculating again and again. And I think what was missing from the last time when I taught you guys about special relativity is that I think I should have given you guys a lot more physical examples on how to work with indices. So I'm going to include a lot more examples when I teach you, so that yeah, it becomes clearer to you. Okay, so our example is, does anyone want to work with me on this, or write down in your notebook? Okay, in 2D Euclidean space. We're only working in two-dimensional Euclidean. I found a few example problems to show you while we go through it. Consider the curve. X is lambda, y is lambda squared. Okay? You need to find the tangent vector. Find the tangent vector at lambda equals 0 and lambda equals 1. What have we essentially said? Well, we're going to find two different tangent vectors. The first one is t here, where we say this is at lambda is equal to 0, and we're going to say we're going to find another tangent vector along this side, and it might look like this.
0 and 2.
So could you tell me what the tangent vector is at lambda equals 0?
0.
Anyone else? Look at the definition of what this would be, and I'm going to give you I'm going to write it out for you. So I'm just going to play it out with you. I'm going to do the first one at lambda is equal to 0, and then you guys do it at lambda is equal to 1. Okay, so the tangent vector t at lambda is equal to 0, okay, is dx over d lambda, and then substitute lambda is equal to 0. And this I'm going to write now with x hat plus dy by d lambda, lambda is equal to 0, y hat. What would this be? Now you can plug this in. This would be 0.
Yeah.
Plus, oh, hang on.
Isn't it P1?
Yeah, it should be 1. So
Yeah.
there should be 1 times x vector hat plus 2 times 0 times y, which is just x vector. Okay, so this is our tangent vector t at lambda is equal to 0. What would it be at lambda is equal to 1?
It would be x hat plus 2y hat.
Yeah, x hat plus 2 y hat. Is everyone clear with that?
Yeah.
Is this clear to everyone? Okay, that's it. It's just that simple. We're gonna, if we have to find a tangent vector, it has to be parameterized by your curve. And remember, this particular thing, we're in 2 dimensions. So our x mu now only runs from 1 and 2. So that's why I've chosen x and y. Okay, this is just a simple baby example. It's not going to be, I mean, we're going to be calculating more complicated things, but this is just a simple example to illustrate what we call our tangent vector. So
Okay,
this
so,
t hat is what we found.
Like, finding tangent is similar to finding a gradient of an scalar value kind of thing.
Yeah, it's just it's almost like a derivative, but we have to understand how it's parameterized. The change is with respect to the parameter of the curve, not the So this is something that's important to note. Like I want to go over this because this is important. When we did this, right? Note how the change for this tangent vector wasn't with respect to my coordinate choice. The derivative wasn't with respect to x or y, but rather it was the opposite. It was understanding how this vector that I've drawn changes with my parameter itself. So this is just finding the tangent vector at different parameters along this curve. So this was lambda is equal to 0, this is lambda is equal to 1. Is it clear to everyone? Even though I've used x and y here, this tangent vector, while it's defined in terms of x and y, is independent of my coordinate system because I'm not finding the change with respect to x, nor am I finding the change with respect to y. Is this clear?
Okay.
It's an important concept. Apurva, Pugal?
Getting it. Can you explain it once again?
No problem. So remember here, I've said that I have a curve. A curve is my one-dimensional object, which is parameterized by lambda. What that is to say is that in this manifold, a curve could be a trajectory taken by a bird in the sky, and how that bird changes. Remember, so the bird's position in the sky returns 4 values of x, y, z, and time, right? And every point in this bird's journey in the sky, it returns to me different values of x, y, z, and time. So I'm characterizing my curve by lambda. So I import lambdas, so that's what I've shown you here. When I import lambda is equal to 0 or lambda is equal to 1, I find different points along my curve. My curve is not changing, the curve is static for now. All I've said is that the curve that I have will return different values based on my lambda. Okay, so all I've said is that this curve that I've drawn here will have different tangent vectors. And the different tangent vectors are uniquely defined at every point. And every point is uniquely determined by lambda. So if you plug in lambda is equal to 0, you'll get one tangent vector. If you plug in lambda is equal to 0.2, you'll get a different tangent vector. If you plug in lambda is equal to 5, you'll get a different tangent vector.
Yes.
And I've given you a small example. So the rule of finding what your tangent vector is by differentiating your vector with respect to lambda. And that's what we've done here. We've taken a small example where I've given you x and y, which is my separation vector here. And I've said x is equal to lambda, y is equal to lambda squared. And to find the tangent vector at different points, you find the derivative of this with respect to lambda and plug in lambda is equal to 0. But the point I was trying to make is that we're not finding the derivative with respect to how x and y or z or time changes. We're finding the derivative with respect to the parameter along the curve, which is why the tangent vectors are independent of the choice of coordinates. It would be coordinate choice. It would be coordinate dependent if I was looking for a derivative with respect to x or y, because x and y are my what do you say? My input. It's my choice. It's my imagination. But lambda is a parameter along that curve. So what I've drawn so far is independent of my choice of coordinates. But in the example I've given you, x and y are a coordinate system that I've given. Is that clear to everyone?
Yes.
Okay, so now we're going to get to something that now should look very familiar to you now, is the notion of tangent spaces. Okay, tangent spaces.
Okay.
What is a tangent space? At any point P in a curved space, we can arrange a Euclidean plane such that it's tangential to the curved space, and any vector that lies in this plane is a tangent vector. And let's just draw that picture for you again. There we go. Okay, so we're going to have a curve here. Let's say there's a curve 1, and I'm going to draw another curve here, 2. Okay, let's say I have a point P on this curve, and I have a point Q on this curve. I'm going to say at every point, any point on my manifold, okay, I'm just going to drop a plane. This plane will look like that. And what I'm saying is that any vector that lies in this plane is a tangent vector to this point. So this is the plane that captures all of my tangent vectors. Okay. Is this clear to you guys?
Yeah.
All I've said is I've generalized my earlier notion of what my tangent vector is, and I said, look, I'm going to be more general and say I'm going to define a space that I call the tangent space. And any vector that I can find, or any vector that can possibly exist at that point P, belongs to this tangent space. Okay? Is that clear?
Yeah.
Apurva? Rachna?
So it's the
Ashmi?
vertical plane. It's the plane like.
Yeah, it's the plane. Okay, so now important point one, which is this might be difficult to comprehend. Okay, but the first point I want to make is the tangent space has the same dimension as our manifold. So it might be tempting to think about a tangent space as, for example, if I have a circle, well, the tangent is, this sort of plane that we have here. So it's very, I mean, you can't visualize a four-dimensional surface, but the idea is that the bit that's tricky to visualize in your head is that our world that is four-dimensional, at every four-dimensional point, we have a four-dimensional tangent space where every possible tangent vector at that point belongs to it. So it's a very difficult picture to paint because we can't draw four-dimensional pieces, so I've drawn it in two-dimensional. And this is something we should be familiar with, right? So now we're going to get to the crucial bit that all of our build-up in the first hour is going to be close to. And this is a statement I'm going to write down because it's important. Okay? In the neighborhood of space around P or Q. Sorry, the neighborhood of space around P and Q can be approximated. Can anyone guess what I'm going to write next? Can anyone guess what I'm going to write next? What am I going to guess by saying? The neighborhood of space around P or Q, what can it be approximated by?
P plus
Tangent
changes,
spaces?
Q plus changes.
Sorry?
Yuvraj, you were saying something.
I told it was, would it be tangent spaces?
No, we are drawing the tangent space. We're saying, what can we say about the tangent space in the neighborhood of P and Q?
P
Apurva was
plus
saying something.
changes in P or Q plus changes in Q.
Sorry?
P plus some changes in P.
Okay, P plus some changes in P. Can anyone else guess what we're going to write down next? Okay, should be clear now.
Oh.
Oh, yeah.
This is everything that we spent the first hour doing. To say that, remember now, so now you should be clear that this manifold that we've drawn here, okay, it's some structure that allows us to define continuity. And what we're going to do and say is that any curve that we have, we don't know. This curve might be continuous, to be honest. Some horrendously complicated curve. And what we're going to say is for any point that we have in the curve, all we can talk about this curve is that it looks locally to be Euclidean. Okay, so this is a very, very crucial point to make. And I'm going to make one small change to this. Can anyone guess what I'm going to replace Euclidean with?
Minkowski.
So this is the beginning of GI. What we're going to see is that whatever curved space you can have, whether you're near a black hole, whether you're near any object of a planet, whether you're near the sun, globally it will look like gravity, but locally the space will always look flat. Okay, but there's another crucial point to make. We're not saying that the space itself is flat, but the tangent space that we associate with every point is going to be flat. So this is important, and the point I'm trying to make right now is all of the crucial physics that we do in the world. Okay, whenever we draw coordinate systems, whenever we draw whatever to understand and do physics, we leave the real world alone. That should be the first thing that's obvious to us. That from the examples that I spoke to you about earlier, the real world we never touch. Whenever we do physics, what we do is we draw up a tangent space. What we draw up is a neighborhood, an open subset, a topological space, a homeomorphism. I'm going to keep, these are all words that we're going to keep used as synonyms. And what we do is we create and construct a local world surrounding that point that we can draw, like Apurva's bedroom, like the Taj Mahal, the Eiffel Tower, a small segment of it. And all the physics that we do is local with respect to that signal, with respect to that chart that we draw. And that's exactly what we've told you again now with the tangent space. Whenever we talk about the world, we leave the real world alone, and all of our physics that we do will involve tangent vectors and tangent spaces. And everything that we can say about comparing vectors and anything that we're going to say about objects in the world will deal with tangent spaces entirely. Okay, so now you can already see the buildup of what GR is going to be about. So you can, I mean, I've drawn this, you can see, right? So P is my tangent space, which encapsulates all vectors that are tangent to that point at P. Q is that tangent space where I've drawn it as a plane. In real life, it's going to be a four-dimensional space itself, which is, I can't imagine it, but that's the physics that we do. It's impossible to imagine because we can't draw four-dimensional charts, right? But the idea is to say that in your room, which is three-dimensional around you, there is a three-dimensional tangent space at every point. Okay, so it's tough concept to imagine, which is why it's easier to picture when I draw it out in 2 dimensions on the paper. But remember that the tangent space that we have at every point isn't really a 2-dimensional flat plane, but it's a 4-dimensional flat plane. And maybe if I draw another chart, perhaps if I draw a different picture, this might appeal to you more. And what I'm going to say is, if I have my points P and my points Q, what I'm going to say around here is this is what it looks like. What are these? Well, these are our old light cones from special relativity. They might be intersected, they might meet, they might be. But the point I'm trying to make is that, yeah, whenever we have our tangent space, you have to imagine it to be a 4-dimensional tangent space, not a 2-dimensional one. Okay, so I'm going to tell you something else now, which is that, okay, this is our tangent space here, this is our tangent space of all vectors here. So now, earlier, right, from all of the physics that we've done with vector spaces, where I've said you can add vector A plus vector B, right? We've said we can add vectors together, and you can do this by taking the ith component that we have and adding together the numbers, right? And then you take the jth component and then you add the numbers together, right? That's how we add 2 vectors. The reason we can't do this in general relativity, and the biggest mathematical difficulty that we're going to have moving forward, is that any vectors that we've defined aren't vectors in the manifold. This manifold here that I have in real world, there are no vectors to be seen. I don't see any vectors in the real world. Okay, all the vectors that you can possibly describe, momentum, the position vector, the velocity, all of those vectors that you usually describe are actually vectors that belong to the tangent space at every point. Crucial to understand this. And so it becomes a problem in GR where the tangent space here, TP, this is point P, this is point Q. So the tangent space here is not the same as the tangent space here. Which means if I have a vector here, I can't compare it to another vector here. There's no way mathematically for me to compare it directly. I need some special structure and I need additional tricks. So now I want you to understand something, right? And hopefully this should now be clear to you why special relativity was important. Okay, so what does this tell us? It tells us, well, the neighborhood, so the global structure of this manifold M is curved. Okay, locally, what does it look like? Well, this point around P behaves like Minkowski space. And this point around Q behaves like Minkowski space, but I can't compare these two together because I need a way to transform between and connect from here to here. I can't directly do it because they belong in 2 different tangent spaces. Okay, so this is a problem that we have to do. But note why this, does anyone understand why this isn't a problem in special relativity and why we can compare vectors in special relativity? The answer is that because our manifold in special relativity is the Minkowski manifold, it means that every vector or curve in our manifold shares the same tangent space. It's the same tangent space. So when the tangent space at every point is shared, by the same thing globally, that's what we call flat. But when every point that we have has a collection of vectors that we really can't compare with the other ones, that's what we call curved space. And the key notion that we're going to do gravity with is to say that every point in that curved space has a small subsection of space which is flat, locally. How local? Well, come back to our definition of our tangent vector. It's local because we've taken in it to be the limit where the parameter that defines our difference in our curve goes to 0. Okay. Now we're going to come to something, I think probably the last two concepts that we're going to do today, which is the notion of vectors and basis vectors as well. Okay, so let me just do that. Any other questions at this point? Does everyone understand what we've done so far?
Just a small clarification. So we can use this idea of tangent spaces to find nearby spaces, right? Like how a neighborhood is defined.
Yeah.
In the counterwise. Okay, thank you.
Yeah, so the neighborhood is in the limit where d lambda goes to 0. That is the neighborhood around which we define a point, the tangent space around P. So remember that here, if there's another point just to the right of P, outside of its neighborhood, it'll have a completely different tangent space.
Yeah.
Which I really can't compare the two together. So there has to be a way for me to understand how a vector like this looks to someone who's in this other tangent space.
Yeah.
Okay. So that's what we're getting to. So a vector, okay, a vector here now, a vector V. Remember, now when you talk about a vector, you can't just say, well, it's a vector. It has to be defined at a point P. So defined at a point P. Let me write that. Let me write it clearly. Is an object that exists in TP, in the tangent space TP, okay? And it obeys the rules of vector addition or multiplication. I think there's a set of things that any vector obeys. I think it's called K-ni-adu, which is like commutativity, associativity, like maybe I'm wrong, but I think there's a list of I can't remember off the top of my head. Vector addition, multiplication, scalar multiplication. I think those are the three things that are necessary for you to define what an abstract vector space is. And that's what this is. We're going to just say it's a vector V is an object that exists in its tangent space, where we can normally, just like we can, multiply, we can equip it with a dot product. And these operations are all legitimate and legal while we're talking about the point P. So only within the point P can we describe this vector. Okay, is this clear to everyone? All I've said is that we've defined a vector at this point P. It's an object which exists in the tangent space. And we've equipped with it additions of adding together two vectors in this tangent space. We can multiply these two vectors in a tangent space. Yeah, so it's just a vector space that we've defined in our tangent space. Okay, the second definition I want to give at this point is a vector field. A vector field, and now we need to write V, and what's the parameter here? X mu. Is an assignment of a vector to every point on my curve or manifold, because it's arbitrary. Does everyone agree with this definition? All I've said is that this, as I slide along this curve, I'm going to have different tangent spaces, which means there's a vector and a tangent space defined at every single point on my manifold. There's going to be one here. There's going to be one here for one particular point. There's going to be something else that looks strange like that, right? So how does this tangent space look? Well, this tangent space has to be a function of x mu. And I'm going to write it as this way. It's V of x mu, which says it's a vector field. At every point on my manifold is a tangent space. Okay, so the crucial point that I'm going to make at this point of time is that two different vectors. Okay, so V of, I'm going to call that x1 mu, and V x2 mu. What does this mean? Well, it's so this is let me call this as x1, which just means it's x mu at lambda 1, and this is x2 mu, which just means it's x of lambda 2, right? All I've said is if there's a vector in a tangent space associated with this point, it does not lie in the tangent space at this point. Is this clear to everyone? It's only, this vector only exists in its own tangent space at that point. Is this clear? What we've done so far itself is a significant achievement. We've said that we can define a tangent space on a curved space. That's not an easy mathematical feat. If you did this and published a paper, you'd get 1,000 citations. It's that important. It's important because it's based on this idea that locally it looks like Euclidean or Minkowski space. Okay, so that's the point. And the difference between this and special relativity is that if you're looking at a vector field, that every vector field shares the same tangent space because it's flat space. In curved space, it doesn't, which means we can't compare. Okay, so I'm going to end with the last concept that I want to do, which is something called a basis vector. Have you guys studied these before?
Yeah, this is comes in like tensors, right? Like basis vectors are the kind of in the vector space. It's like they are the points in the vector that doesn't change when you like change your coordinate system type. When you stretch your
The basis actually changes. The basis does change.
The bases are the one which helps us to determine. Those are the unit vectors.
Sorry, like they lie in this. Okay, I quite forgot what actually it was. Yeah.
No, but Apurva was right. Apurva said the basis vector is what we call the unit vectors, right? And the basis vectors are, remember, so this in red is where you should write down this. When I first say basis vectors is now when we're saying we're making a choice of coordinate. When you choose a basis, that's making a choice of coordinates. Whereas the physics up to this point is independent of our choice of coordinate. What we're going to do is introduce coordinate systems through basis vectors. Why do we do it? Because abstract spaces, we can't do calculations. So if you want to do calculations, the price to pay is to introduce a coordinate system. Okay, so Apurva was right. A basis vector is just a set of unit vectors at every point. So that's exactly what we're going to do. So we're going to say at our point P. So I want you to remember this picture in your head, or write it down and refer to it again and again. And what I'm going to say is at this point P, point P, there's my tangent space. What I'm going to say is at this point P, I'm going to define a set of vectors, set of unit vectors, you can say, at P, and we call them, this is the mathematical notation E. Okay, this is what it is. This is essentially what I'm trying to say at this point in time is if I'm looking at my tangent space, I'm going to break this tangent space by introducing my coordinate system. And I'm going to say this is my E1 and this is my E2 vector. Or you can think of it as I hat and J hat. A is your dimension of the space, which will be 4. So in our space, which I've actually only drawn 2 because we're working in our space, we're going to have 4 basis vectors from 0, 1, 2, 3. And it changes at every point. At another point on our curve, we're going to have a completely different tangent space, and the basis vectors are going to be completely different. It's just like how if this is our coordinate system to us, you might have someone else who's working a coordinate system like this, right? Is everyone clear? This is the notation. We're going to call our basis vectors, instead of I hat and J hat, we're just going to call it E. E1, E2, E0, E3. Is this clear to everyone?
And they all should have a common originating vector.
What?
Like everything.
Not clear.
Okay, like everything begins from passes through a common point, like begins from a common point.
Yeah, everything is defined point-wise in our space, which is, again, if it's not global, the words you're going to use in your dictionary are local and global. So if we define points at every point, it means it's local. It does not hold for the entire manifold. All the physics that we can meaningfully talk about are in this Kuti subsection here, in that tangent space. Okay?
Okay. Fine.
So now the idea is I can choose my basis vectors to be of any kind. Like if I'm a professor and I particularly want to annoy my students, I'd set you homework where instead of I hat and j hat, which are nice 90 degrees with respect to each other, what if I had a coordinate system that just looked like this? What's stopping me from having a crazy bad coordinate system? I can do it. It's just poor choice. What I'm going to choose to do is to say that my basis vectors are orthonormal, which is to say that there are nice, beautiful 90 degrees with respect to each other. The magnitude of the unit vectors are also 1, right? That's what we've worked with in the Cartesian system, and I'm just going to say we're going to continue to use that with our basis vectors. So if our basis vectors are orthogonal or if they're linearly independent, we can write any vector that's in my space here, my tangent space, the sum vector here. Okay, I can write my vector in my basis. And here's how I'm going to do it. I'm going to write it as VA, EA. And immediately, guys, I want you to tell me what convention do you notice and remember from special relativity? Does anyone not remember or see anything with my indices that I've written down just now?
The Einstein summation convention.
Exactly. Okay. So we've written down the Einstein convention, and what are we going to say with this? Well, it just means that we have to expand this.
Oh, yeah.
Right? That's what it stands for. And let me give you a better example. Let's say we're working in a two-dimensional space where I'm going to say for simplicity, we don't have time and we don't have our z coordinate. Well, what does this become? This just becomes our coefficient times our I hat vector and our second coefficient times our j hat vector, right? But I and j hat are the things that are my choice. I could even say, well, this is v1 times my r vector and my theta vector. If I'm now looking at, what do you say? Well, if I'm looking at polar coordinates, right? So the choice of what E1 and E2 are completely different. We could have spherical coordinate systems, cylindrical coordinate systems, all kinds of weird coordinate systems that you choose to work in depending on the object that you're studying. Like Cartesian coordinates are useful, but the reason we work with polars sometimes is if we're working with an object that has spherical symmetry, it might be more convenient to talk about a coordinate system with r and theta. And we're going to work with many different coordinates. Okay, but the idea is that the coordinate choice is independent. So not now. This fundamental vector that I have here is an abstract vector. It's just roaming around in the space. It just lives there. But for me to meaningfully talk about it, I'll replace it by, I'll give it a basis. This basis is my choice, which now you should now write in red. And once I have my choice, I can express it however I want, which, if you remember, could just be something as 5i plus 6j. That's all I've written down so far. Right? Is this clear to everyone?
Yeah.
Okay, so now what I'm going to say, let's see. I think I'm going to end today's session with understanding what the metric is. I'm going to get to that soon. Okay, so now I'm going to say I'm going to choose a particular set of basis vectors, right? Which is E. I'm going to call them mu because remember now we have 4. We're not going to only work with. Whenever you see the mu, you remember you should be thinking 4 vector. So now we've got our 4 vector basis, and I'm going to define it as following. And the limits where okay, I've written down a new definition of what this is a particular. I'm going to circle this in red. I'm going to say this is a useful set or a useful choice basis. Why is this a useful choice of basis? All I've said. Now, what have I defined here? So here you can see that this is actually 4 equations. If you remember, the exercise we had given each other was to identify the indices that we're looking at. So these are 4 equations for the 4 basis vectors. And what does it tell me? All I'm saying is, remember, if I have my curve here, I have my point x mu and another point here, which is parameterized by lambda, remember? And this point here is x mu lambda plus d lambda, right? That's exactly what this statement is. We're looking at two different points in the curve, and what did we call the separation vector? This thing, the vector which is the separation between 2 points on my curve, and I called this delta S, a small segment of my separation vector. And guess what I've done? Sneakily, all I've done is I've introduced a familiar calculus, what do you say? Familiar calculus tools, and I've said we're going to use that to define our basis. So guess what I've done? I've said I'm going to define my basis, let's say I, the E1, which you can think of as the I hat vector, if you want. I'm going to define this. Let me just write this out. The limit where dx1 1 goes to 0, and this. This was x. Okay, so 1 second. If I write down for you guys to understand, if this is t, x, y, z, 1 is x, right? So I think I'm going to use 2 so that we don't use, we confuse ourselves. So what is 2? Y. That's the index 2. x2 is y. So if I go back to our definition, E2, which is y hat, is the limit where the x2, y goes to 0. The change in the y coordinate goes to 0. How our separation vector changes with dx2. This I'm going to rewrite now as y. So guess what I've done? All I've said is a useful choice of basis is to define my basis vectors by just taking the derivative of my separation between 2 points with respect to t, that's 1, with respect to x, with respect to y, and with respect to z. You see why it's a useful one? It allows us to use calculus, and it ties in everything that we've been doing so far. So all I've done is I've defined my orthonormal set of coordinates. It's going to look like this. I can call one x, I can call one y and z, and there's one, like a fourth dimension of time. And all I've asked is my separation vector, how does it change with respect to x? However it changes with respect to x, I'm going to call that my I hat. However it changes with respect to y, I'm going to call that my j hat. Right? Is this clear to everyone? It's a useful choice of basis. You can use any other choice of basis that you want. For our calculations and everything that we're going to do, this is a useful set of bases. Is this clear?
So here we have a point defined by two different vectors, and now instead of using matrix and finding the changes,
No. We're looking at the same point, and we're looking at a point in the neighborhood of that point. So I'm looking for a small separation in my curve. Meaning, if my curve is like this, I'm just looking for a putty, like here. That's it, like a small interval in my curve. And for me to understand in my tangent space how to draw a basis, I'm saying how my separation changes from this point to the next in the x direction that I call. I'm going to treat that as my x vector. How it changes in the y direction that I call y, I'm going to call that y. So it's a useful choice of basis. I want you to go back home and think about this, because that's the choice that we're going to be using for our course.
but I think the basis vector will remain the same. It's just the points which are changing, right?
No, but the basis vector is defined at every point. So I'm saying I'm defining my x by how this point changes with respect to my x coordinate. Essentially, what this is saying is that if my curve look like
it
this,
says that every point is viewed from different points.
this is what it looks like essentially. Is this clear? Like this, think of this as your coordinate system. Right? I'm trying to define a good orthonormal basis, and I'm doing it by looking at the separation vector from this point to this point. And that's how I'm doing it. That's the picture I've drawn here is essentially what we've done here or here.
Every point will be the origin, right?
Every point will be the origin for that particular point. Yeah.
Yeah.
But remember, we can't. We can't. So remember, this point has its own tangent space. This point has its own tangent space. I'm running out of colors. This point has its own tangent space. This point has its own tangent space. So we can't compare them, but this gives us a useful choice to define vectors in its own tangent space. Essentially, what I've told you here is my vectors that I've drawn in the tangent space can be written in any choice of basis. I'm saying a convenient choice of basis is Cartesian. That's all I've said here. That's it. That's all. I'm just trying to say that my vector, which is an arbitrary vector in that tangent space defined at every point, I'm just going to say what this statement I've made here is, it's just saying Cartesian. For every point, unique Cartesian system. That's all I've said. Like whenever I have a tangent space and a vector, I'm just going to drop a Cartesian coordinate system to understand that vector. Does this make sense?
Yeah.
Remember, this is defined at P, and you'll have a separate. This is the same equation, but it'll look different when you go to P plus delta x. Okay. Now another interesting point and a comment. I want you to go home and see whether this makes sense. I'm going to leave it as an exercise. Okay. If we were to choose a curve that connects P and connects Q, right? This is my curve, and we choose this curve in a way that it only varies in one coordinate. It only changes with respect to one coordinate. Then I claim that this that we had here is the tangent vector itself. At that point. Okay. This is a choice. So it's not real physics, but I'm choosing the basis such that my going from one point to the other, it only varies in one coordinate, and that's what we call the tangent vector. So this is just a exercise for you to do at home. All you have to do is pretend like some of these derivatives vanish and go to zero, and you're only left with one derivative, and you have to argue and see whether that same one derivative is the same as my definition that I've done here. Maybe it's already evident and clear, but essentially what I've said is if you vary it only in one coordinate, my basis vector becomes the tangent vector. Okay? And if I do this, does this make sense to you? I'm just going to, essentially what my assumption is saying that ds by dx is 0, separation vector with respect to y is 0, separation vector with respect to z is 0, and all I'm left with, sorry, I'm not writing. Yeah. 3 of these are 0. I've chosen. This is a choice. So it's not real physics. It's choice. And I'm left with one coordinate. And I can choose that coordinate to be lambda. And remember this. The definition of this thing was our tangent vector. That's what I've claimed just from this here. I've eliminated 3 out of the 4 derivatives. And the thing that's left makes it a tangent vector. Okay? So what does this let us do? Well, remember, if a separation vector is our change this way. Okay, and now all I've said is that we've eliminated 3 of them, so this actually is left with 1. No, this is actually definition of, what do you say? Here, going back, plug this into here. Can everyone see this? This one. This one. The change with this separation vector with respect to x is what I call my basis vector. So all I've said is my separation vector is, yeah, dx. Is this clear to everyone? All I've done is I've taken this here and I've substituted my choice of basis into this. Okay, so immediately you can see that this ds is what I call it's a vector. Why is it a vector? Because this E has a vector on top of it, but these indices are summed. So essentially this is E naught dx naught plus E1 dx1. Yeah, is everyone clear with this? Now we're going to end today's session with one last idea. This is, here all I've said is if I have my separation vector, a small one, I can expand this in a basis. Remember, this was our starting definition. If I have V, I can expand V as this, right? Does everyone see this? Does everyone remember this? All I've done is apply the same thing to my separation vector. So if I replace V with ds, what does this become? Well, VA now becomes DSA. But what is DSA? Well, DSA is just dx mu. How my separation vector changes. Does everyone see this? Is everyone happy with what I've written down right now? All I've done is I've expanded my separation vector, infinitesimal separation vector, into a basis. A convenient choice of basis, a Cartesian basis. And now finally is the ending point of today's lecture, which is that I'm going to do a dot product. Given that it's a vector space, I have a dot product. I'm going to take a dot product. And can someone tell me what the dot product in geometry represents?
Area.
Is it the area?
Cross gives us the area. Dot product.
It's the length, isn't it?
Length.
It's the projection of one vector along another. Right?
Over the other.
Yeah. So what we're going to do, this is the inner product. Okay, so this is what we call ds squared. And what is this going to be? It's going to be e mu dx mu. Remember the good habits session that we had? If you have repeated indices, I can't write the same repeated index. I'm just going to write a different one. Yeah, these are both, what do you say, the Einstein summation, but I've written different indices because that's good. It's good practice, right? And this is dotted. And now what I'm going to do is I'm going to write this as okay.
Can you explain me why again it's good? Because I'm not getting.
Sorry, what do you not understand?
We use different indices, right? You said that it's good.
Okay, cool. Okay, so the reason I've good habit, and I'll get back to this in a bit. Good habit in GR, you will have to work with 40 indices, okay, or more. Meaning when you're doing GR for real, you'll have mu, you'll have rho, you'll have sigma, you'll have gamma, you'll have delta. You'll get so used to writing Greek indices that you can write it better than English, okay? And because we're working with many indices, remember these represent sums. We have a convention, a summation convention. So it's just like how if I had two variables, and if I'm saying if I'm doing xi times some, let's say xi times yi plus, you could do it this way. Or yeah, so if I have one sum and I have another sum somewhere, let's say xi times yi. If you want to multiply them, the idea is you probably have two different sums, right? Like I and j, and you'd say, well, this one you'll call I and this one you'll call j, right? If that's not clear, the point I'm trying to make is that these are all sums, so I don't want to be confused by writing the same index again and again. Like if I write x mu plus x mu, remember this is a different sum over this one, but if I write it with the same index, I might get confused because I'm writing 0, 0 plus 1, 1 plus whatever, and that should be separate from my computation that I'm doing here. So it's just a good habit whenever you're writing indices, if you have more than one repeated, okay, give it a different name, just so that you're not confused yourself. Okay, that's it. So you're essentially reminding yourself that I have to sum over here and sum over here. It becomes confusing when you have quantities that are multiplied together. This is a horror story. Like, I don't know how to interpret this, but you'll interpret this better if you have this, because you'll know that, okay, I have to do that separately and I can do this separately and then I have to still multiply them together. But if you write it out as one, it's a terrible habit and you'll get confused with, with the answer that you're writing down. So the point I was trying to make is I'm taking my separation infinitesimal and I'm going to multiply it, dot it with itself, which remember should give me, it's the inner product, square of the inner product. And what do I call this? ds squared. And what should this be? Well, if you go back up here and you look, ds is this. Yeah. And I'm dotting it with this. Right? That's all this is. I've taken the definition from here. Okay. And I've just asked myself, what's the inner product of that infinitesimal separation vector in my basis? I've expanded it in my basis. And I've asked, what is it in my basis? And I've got this down here. Okay. And we should now ask, what is this equal to? Well, I can take here. Remember, so out of these, dx mu and dx nu are just numbers, right? The other two things are just vectors. So they're the ones that get dotted. And now you should start to see something that's familiar whenever my tablet decides to sync. Sorry, my tablet isn't syncing for some reason. I'm just trying to figure this out. Can everyone still hear me? Is there a problem with my net?
Yes, we can hear you.
Ah, there we go. Okay, so now you should immediately see the glory that we've just done. We've defined a tangent space. We've defined, expanded our separation vector with a convenient choice of coordinates. And what we've done is asked ourselves, what is the inner product of that separation vector with itself? And look what we find. Does everyone remember this?
Yeah.
This is the metric of space-time. This is the metric that's the fundamental quantity of all of general relativity. And all we've said is ds squared, if I use this definition. That's all I've written down. We've recovered special relativity just by applying the principles of local Minkowski space. What we've done is asked ourselves, what is this infinitesimal separation between a point and its neighborhood? I've asked myself, what's the inner product of that point with itself? I've chosen a convenient set of bases that allows my coordinate systems to be locally Cartesian. And what does it spit out? The fundamental equation of special relativity. Right? So if our basis vectors that are flat in special relativity, this thing is equal to eta mu nu. But in general relativity, we're going to assume that it isn't eta mu nu, and we're going to call it G, which is to say that the dot product of two vectors, right? If it was Euclidean, what do you think this would look like in Euclidean space? I think it's worth going over this. This thing here are 16 dot products. I can enter 4 values here. I can enter 4 values here. And if I was in Euclidean space, what would x hat dot y hat equal? What would x hat dot x hat equal? Can anyone tell me quickly?
First thing is 0 and second thing is 1.
So now you'll start to see that if we were in Euclidean space, this would be 0. This is 1. What would y with x be? What would y with z be? What would y with y be? Cool. So you'll now start to see that if we were working in Euclidean space, this would either be 0 or 1, right? And from our homework and our exercise, immediately you should say that in Euclidean space, based on our definition now, this thing is just the Kronecker delta.
Oh.
Right? Now, I'll say, okay, we're not in Euclidean space anymore. Now we're working in Minkowski space, right? So what is time dotted with time? And remember, we were working with dot products. So remember, there's a, and what is space with space? Do you remember? We did this.
Some projection.
They're the same. So t with t was 1. And if you remember this, we said, well, to do a dot product, you actually need a row vector and a column vector, right? Remember we did this. We said that, oh, well, hang on. 1 will be a plus, 1 will be a minus. And yeah, remember there was a minus sign, crucially, a minus sign in Minkowski space. So if we work in Minkowski space, this thing doesn't become the Kronecker delta, it becomes
Eta mu.
Yeah. So it turns out that when we're working in general relativity, we're going to come across fun, exciting ways of combining these basis vectors, and it'll never look like eta mu nu ever again. It's going to look like G mu nu. And this G mu nu that you have here is what we call the metric of space-time. And how do we find these? Well, they're not just random in general, but if you solve Einstein's equations, you arrive at this as your final answer. You arrive at what could be a potential candidate metric, and with that you do fun physics. Because if you remember now, what does the metric do? It tells you this thing here. It's the invariant length. You should now start to relate concepts that we've done now with special relativity. Once you find a G mu nu, right, it tells you that the distances between two things, the separation vector takes up different forms, right? But remember that the metric itself is, well, it's based out of the basis vectors that we have. So what does it do? It distorts our distances, but what does it leave invariant? The length. So this is how special relativity is encoded into GR. It says that in the length between space-time, everyone will agree on what it is. But it'll be different based on the metric you're working under in the space that you're in. And this is why it's general. It's general because we no longer assume it to be Minkowski space. Okay, so I think that's a good point to end it today. I have about 5 minutes. Any questions?
I don't have any.
Okay, I wanted to say, like, these are pretty fundamental ideas. I don't think they could be, I'd urge you to respect the subject. Like all of you said you wanted to do general relativity, all of you said you want to work in gravity and work with black holes, but we respect the subject because these are not ideas that you can learn in an hour. Like I didn't understand indices the first time I worked with them. It took me at least a year, whether that's embarrassing or not. Like it took me a year to be fully comfortable with trying to understand how to manipulate them, how to rewrite them, what are dummy indexes, what are free indexes. So I'm trying to say that this is something that you get comfortable with only with practice. And I remember when I started writing it on GR, like writing down these indices was really like unfamiliar. Like I'm like, shit, if I'm writing dx, is there a mu there? Is it a nu? What am I doing? What am I doing? So I'm trying to hopefully give you the habit that try to look at what the index signifies. If you see an index, you know, okay, it's a part of a vector. If you see a repeated index, you can say, it's being summed over, which means it's a contracted index, which means on its own, it's a scalar. If you see two indices, just like how we just saw here, when all of you that asked what a tensor is, this is the definition. When you dot two basis vectors like this, you don't know, this is what a tensor is. It's something that you arrive at by dotting two basis vectors together. And now you'll understand immediately what I gave you the earlier examples of. If you feed in one new vector in this, which is VA times, I'm going to call it a basis vector called psi. Well, if you dot the tensor with one, you'll end up with a new dot product. And it'll spit out one vector, this one. Right? What if you give it two vectors? Well, if you take E mu dot E nu and you dot it with two other ones, psi mu, psi nu, what will you end up with? You'll end up with a number, some number, let's say 5. And that's the definition of a tensor. Tensors aren't difficult to understand. Tensors are just you taking your basis vectors that you had earlier and dotting them together. And guess what? Then you can have more tensors. This is you just saw a tensor of rank 2. If you see a tensor in GR, we're going to get to something called the Riemannian tensor, which looks like this. Okay, something like this. And immediately you can say, well, this is not really that scary. The tensor is just what you expect it to be. Is going to be something like E mu dotted with E nu dotted with E lambda dotted with E rho. It's just this. It's 4 vectors and I'm taking together, and I'm trying to understand and make sense of it. So then what I'm going to do with you guys next time is try to understand, well, hang on a minute. Last time we said that if we want to work with an invariant quantity, well, not only can we work with a contravariant vector, we also need something called a covariant vector, which then means that if I have a vector like V, I should be able to not only expand it as this, but I should equivalently be able to expand it like this. And then we'll say, that then means that this basis vector that I have and my tangent space at P, which is TP, has a dual space associated with it called T star. And that says that every vector in one, which is a row vector, has a column vector in another space, which are connected to each other by this thing here. And we're going to do that next time. And once we get there, I think you'll hopefully understand what tensors are, and I'll give you homework with how coordinate systems change and all of that. Any other questions?
Sure.
I have 2 more minutes, and I have to go, and I will take questions over text. Any other questions? Apurva, Rachna, Ashmi?
I suggest some articles to read upon tensor space and vector space, vector field.
I'd suggest your homework for this week is not going to be any conceptual, like mathematical homework, your homework for this week is to go through the entire 3 blue, 1 brown series on linear algebra and what vector spaces are. So I'll link you to that playlist. There are beautiful 15 videos on what vector spaces are, and I think you'll understand what basis vectors are, what eigenvalues and eigenvectors are at the end.
So vector space is a vector field.
Yeah, a vector field is a quantity where at every point it returns a vector. A scalar field is something that at every point returns a number. A vector space is my tangent space. I've taken a tangent space saying at every point I can associate a space to it where any vector that's a tangent vector to that point must lie in this space. And the space is equipped with what I call vector addition, vector multiplication. And yeah, that's my definition of a tangent space. A tangent space is my vector space. I'm also going to say that there's a dual. And this word dual used to scare me when I was first learning physics because I was wondering what a dual is. And that's the homework. The homework is going to be you guys looking through 3 blue, 1 brown's channel and understanding what's going on. Cool?
Okay.
Cool.
Okay, I'm going to go now. So send me messages on WhatsApp. I like messages.
Sure. Yeah.
Okay, take care. Have a good Sunday.
Yeah.
Thank
Thank
you.
you.
Bye.
Same to you. Bye.
See you.
Hmm. Yeah. I have some work right now. Yeah. That's what. Yeah. Yeah. Yeah.